Hi everybody, welcome back. This is the second part of the second lecture of the stats content of the dyspepsia module. So before the break we were looking at these general really important ideas of the hypothesis and how we test a hypothesis by generating a p-value. And then I talked about how in science in general we tend to be either looking for differences or trends. And now in this next part I want to look at how we can actually test for a difference. And we're going to look at a couple of different tests. In part 2 we're going to look at the t-test, and then later on we'll look at the chi-squared test. So there are really kind of two sorts of difference that we might look for in data. The first is a situation where we have a quantitative measure. How long is a piece of string? How tall is a person? What concentration is a particular enzyme? And we want to compare two different categories. So we want to compare males and females, or one species of bacterium and another species of bacterium, or one drug and a control. So we have two categories, or more categories possibly in other situations, but in the case we're going to look at today, just two. And then we have a quantitative measure for each. And what we want to know is the average quantitative measure for each of these two categories the same, or is it different? So you can visualize this on a frequency histogram like this. Imagine we have two categories, the blue and the green. They might be men and women, and we've measured something, it might be how tall they are, and we want to know, is there a difference? So are men taller on average than women or not? The other scenario is where we, instead of having a quantitative measure, in fact we have frequencies of categorical events, or frequencies of individuals that fall into different categories, and we want to know whether those frequencies are different between other categories. So for example, we might have this kind of situation where we're looking at two events 1 and 2, two different types of event that we've counted up in two different types of patient, category A and category B. So again, these might be male and female, or people treated with a drug and people not treated with a drug. And then we might be looking at the frequency of a particular outcome. Did they get better or not? So we end up with a bunch of frequencies for each combination of the treatment and the treatment and the outcome. So in this situation, we're going to need a rather different kind of test. So we're going to look at these two scenarios in the two parts of the lecture coming up, concentrating initially on this situation where we have a quantitative measure and we want to compare it between two or more groups. So to keep things simple, we're just going to think about two groups for the time being. There are situations in which you might want to look at more groups, and there are tests that would handle that, but let's focus on the simple case. So what we want to know is really whether the means, which we often indicate using this X bar type symbol, whether the means of the two samples, sample 1 and sample 2 in my example here, are significantly different. Are they really different, or is any difference that we see simply the result of random sampling under a null hypothesis in which the two samples are actually the same? So we're going to use rather than just kind of eyeballing the data and making a subjective decision, we're going to make an objective decision based on a statistical test. That's what the test is going to do for us. It's going to help us make this decision. So let's look back at this key idea of a population and a sample. In general, in science, we can't access data from every individual in the population, so we're going to take a representative sample, and when we're comparing two groups, what we're going to need is a representative sample from each of those groups or subpopulations. So we're going to take a sample and get a sample mean from each of our two groups, maybe men and women, or people who've been treated and people who haven't, and we're going to look at those as being representative of the underlying populations, each of which have their own means as well. So the terminology here, the sort of notation, we've become used to seeing X bar as the mean of a sample, and using the subscripts 1 and 2 we can now differentiate between two different samples. But those samples are supposed to be representative of two underlying populations, if you like, all of the men in the world and all of the females, or all of the people who could possibly have been treated and all the people who haven't. And to differentiate between the true underlying mean of the population and the sample, which is only some of the individuals being measured, we use the Greek letter mu to represent the whole population mean, whereas the the Roman letter X represents the individual sample. So our X bar 1 mean of a sample 1, is supposed to be representative of the underlying population mean 1, mu1. So this is the Greek letter mu, and it's typically used for the mean in stats. Okay, so let's think about what hypothesis we would have in a situation where we're trying to compare two samples, trying to find out if they're significantly different. Well, the null hypothesis says that nothing interesting is going on. There's no effect, there's no biological effect. In other words, it says that the two means, underlying population means, are identical. So regardless of any random chance events that happen when we sample, which will probably mean that our two sample means are not identical, our assumption in the null hypothesis is that the true underlying average or mean value on our variable that we've got is the same for the two groups. So if it's men and women, what we're saying is that the average value of this variable for the men is the same as for women in the underlying population. We then collect some samples and we want to know whether those samples are consistent with this null hypothesis or whether the alternative hypothesis is true. And the alternative hypothesis says that the true underlying population means of the two groups are actually different. So mu1 does not equal mu2. Okay, so in this situation, our null hypothesis is and our alternative hypothesis are two-sided in the sense that we haven't specified which direction we think the difference might be. So we've said the null hypothesis is just there's no difference, and the alternative hypothesis is, well, there is a difference, but we haven't said which way round. We haven't said, for example, men are taller than women, or the drug leads to healthier patients than no application of the drug. So for each alternative hypothesis here, there are two possibilities. Mu1 could be greater than mu2, or it could be less than mu2. In other words, the mean, the true underlying mean for, let's say, the men might be greater than the women, or it might be lower than the women. Either of those is consistent with this two-sided alternative hypothesis. That's what we mean by two-sided. Both alternatives are possible. But that you can have studies in which you're really focusing in on just one kind of difference, in which case your alternative hypothesis is specific and one-sided. So it either says one of the populations has a lower mean than the other, or it says one of the populations has a higher mean than the other. These would be one-sided hypotheses, and they have reciprocal null hypotheses to go with them. So if your alternative hypothesis is, let's say, men are shorter than women, your null hypothesis is that men are either taller than or equal to women in height, for that example. So the null hypothesis says it's not happening, there's no effect, and in this case, by effect, we mean the first mean is lower than the second, and the alternative hypothesis states the alternative, that there is a difference, and in the case of one-sided hypotheses, it says it's in one particular direction. Okay, that turns out to be an important distinction because it does affect the results of the test that you do, and it's up to you as the scientist to decide in advance whether or not your hypothesis is one-sided or two-sided. Okay, whether or not it's one-sided or two-sided, a key property of the null hypothesis and the alternative hypothesis is that they should be mutually exclusive. So in other words, if one of them is true, the other one cannot be true, and vice versa. So, for example, if we're going to use the alternative hypothesis that the first mean is less than the second mean, men are shorter than women, say, then that is completely mutually exclusive with the alternative hypothesis, which is that the first mean is greater than or equal to the second mean. And so that should apply whichever form of the hypothesis you use. So if you use a two-sided hypothesis like this one, you say the null hypothesis is that the first mean is equal to the second mean, and the alternative hypothesis is that the first mean is not equal to the second mean. Clearly, both of those two things cannot be true at the same time. Right, so that's quite abstract and quite difficult to get your head around, so it'll be a lot easier to understand, I think, when we look at a real example. So let's look at a real example using a drug called triantarene, which is a diuretic that's used to treat blood pressure problems, hypertension. And when it started being rolled out as a treatment, people started to notice it did something very odd, or it seemed to be doing something very odd, and that is turning people's urine blue. So, like in this delightful sample here, we appear to have patients being treated with a drug whose urine has turned blue. But obviously, being good scientists, we want to know, is this just a chance event? Maybe something else going on in that particular patient, or are we really seeing an effect of the drug? So we're going to do an experiment where we treat patients with triamterene, and then we have a control group, which are randomly selected not to receive the drug, and then we're going to measure how blue their urine is. So you can measure that using a spectrophotometer, and we can measure the absorption of blue light on this axis down here, and we can get our two groups of data points, one from the control group where they're not treated with the drug, another where they have been treated with the drug, and then we can assess whether or not how blue the urine is really significantly different between these two groups, or if any difference that we see is perhaps just a chance event under the null hypothesis, which says that there's no difference. So first of all, in order to run a statistical test of this idea, we need to define our null hypothesis and our alternative hypothesis. And so for this study, what we're going to do is we're going to say that the null hypothesis is just that the amount of blue colour in the urine is the same for the two groups, the controls and the triamterene treatment. And the alternative hypothesis is that there is some kind of difference. And we won't specify for this study whether the urine in one group should be greater or less, so to have more or less blue colour than the other. We're just going to make it two-sided. We're going to allow for both possibilities. So it could even be that triamterene makes your urine less blue. So we're going to allow for that possibility. If we don't allow for it in the hypothesis, then should we find the data go in that direction, we wouldn't be able to reach any conclusion about triamterene reducing the blueness of your urine. So we're going to leave ourselves the opportunity to find either option in the data. So what do? We want to perform a statistical test ultimately that gives us a p-value, a probability of the data that we've observed if the null hypothesis is true. So we've seen a bit of a difference in the colour of the urine. We want to know how likely is that if the null hypothesis is really true and there is no true effect of triamterene on the urine. So to calculate that p-value, which is the probability of the observed difference if the null hypothesis is true, we're going to use, first of all, a test statistic. So we're going to calculate a thing called a test statistic, which measures actually the size of the difference that we've observed, and it has known mathematical properties which allow us to calculate a p-value from it. And most of the heavy lifting here is going to be done by a computer. It will be calculating p for you, but I am going to show you what the test statistic is and how it works for the test that we're going to use, because it illustrates important points about how statistical tests work. So the test we're going to use is called a t-test, and in fact it's often referred to as the student's t-test, not because students use lots of t-tests, but actually because it was originally designed by a guy who worked for Guinness, the company that makes beer, and he was set a task to try to establish whether or not some change in the manufacturing process improved the beer. I don't know, maybe he was looking at the colour of it or the taste or whatever. And he decided he wanted an objective way of testing for this difference. So he developed the t-test that I'm going to show you. And he was working for a private company, so typically they wouldn't want that information to be in the public domain, the work that had been done by their employees. They want to keep hold of it and keep it secret. But the guy was so excited about this test, he wanted the world to know about it, so he published a paper in which he described it. But in order to disguise his identity, he just called himself Mr. Student, in order that his company wouldn't find out that he'd released this information. Anyway, that's an aside. So this thing called the t-test is going to be our way of making an objective assessment about whether the quantitative measurements we got from these two different groups are significantly different. And this t-test, as the name suggests, uses a test statistic called t. So t is a thing that we're going to calculate which measures how big the difference is between the two groups, and it has known mathematical behaviour so that we can use it to directly calculate a probability, a p-value. So the t-test goes by slightly different names. Sometimes, like I say, it's called the student t-test, sometimes it's called the independent samples t-test. There is another version of it called the paired t-test, and we're not going to deal with that in these lectures. It's a different test. It's similar, but it deals with a slightly different situation. So watch out for that. If you see a paired t-test and you're trying to do what I'm describing today in today's lecture, then avoid it. You want the independent samples t-test. Specifically, a paired t-test is, as the name suggests, dealing with data that are paired. In other words, where your two groups contain data points that are linked in some way. So in a medical situation, very often the link might be the same patient. So you might take a measurement in a patient and then apply a treatment and then take another measurement. So the two data points are from different conditions, like let's say before and after the application of a drug, but they obviously share something in common because they come from the same person. So that's important in terms of how we do the test and what the conclusion is we reach. So the test we're talking about today is for situations in which the data in the two groups are independent. They're randomly selected separately as two different groups rather than sharing something in common in pairs. Okay, so let's have a crack at opening up this t-test thing and trying to understand what it does. So the t-test involves calculating a statistic called t, and it has this rather ugly looking equation which allows us to calculate t. But it's not that complicated when you look at what's under the bonnet. The most important thing in this t equation is that it measures the difference between the two means. So in our example, we've calculated how blue our control sample is and our triantrene sample. And we obviously, in order to work out the probability that we've observed the difference we have observed under the null hypothesis, we need to work out, well, how big is this difference? And we do that mathematically by calculating the difference between the means. And all that we then do is we sort of scale that difference according to two other bits of information that we have about the data. One is the sample size, because the bigger the sample size, the more confident we're going to be that these means are good estimates of the underlying population means. So we want a t-statistic that responds to sample size as well as the actual difference we've observed. If we see a big difference and we've got a big sample size, then we're going to be seeing a scenario which is really unlikely under the null hypothesis, because if you've got a really powerful test, big sample size, and you're still seeing a really big difference between the two groups, that suggests it's a real difference, not just coincidence. And the other bit of information we need is the variance. So the variance in our samples is how variable the individual measurements are within a group. And in the case of our urine, if we find that every patient varies wildly in terms of how blue their urine is, it's going to be more difficult to spot a true difference between the two samples against all of that noise. So we need to take into account that noise by putting it into this equation here. So t is basically scaling the difference that we observe by the amount of variability and the sample size. Okay, so we can go ahead and calculate t, and if you think about it, t could actually come out as either positive or negative depending on which way round your means are. So if the mean of the first group is greater than the second group, then you're going to get a positive difference and a positive value of t, whereas if it's the other way around, you're going to get a negative value of t. So that's important when you do a t-test and you see the value of t, whether it's positive or negative tells you which way round the means are, and that should be self-explanatory, but it's worth noticing it. So what matters really in terms of the significance of the difference we've seen is not whether t is positive or negative, but how big it is. So the absolute value of t, which we might represent like this, t with two straight lines down the side, how far away from zero it is, whether it be positive or negative, that's the thing that tells us whether our difference is going to be significant or not. So imagine some different scenarios. I've sort of graphed out some different scenarios. In this scenario here, we've got the blue and the green sample, let's say the triamtrene sample and the control. And there's a relatively big difference between the means of these two groups, and the variability in each of the groups is small. So these bell curves are really tight, so most of the measurements in one group are all tightly clustered close to the mean. So in that situation where you've got small variance and a big difference, we know from the equation for t on the previous slide that we're going to end up with a big value for t. And that's the whole job of t. T's job is to represent our kind of confidence that there really is a difference. So when it looks like this, you can see from the graph, it looks like these two distributions are very different. These two samples really do look like they're different. So we get a big value of t. But at the opposite extreme, and you can see there's intermediate scenarios on this slide too, but if we go to the opposite extreme where there's both a small difference between the means compared with our previous example and a big variance in each of the two samples, lots of scatter among the measurements within each group, Now we're a lot less confident about this difference, perhaps just having arisen by chance. So the t value is much smaller as a result, and you can see that if you look at the equation on the previous slide, you'll see how t gets small when the variance is big and when the difference between the groups is small. So t is responding to these different properties of the data in such a way that it allows us to directly calculate a probability, a p-value, which is going to make sense of our results. So we can look at the example and see how this works. So here's our plot of the two samples for the control patients and the triamterene patients. And what we want to do is run a t-test to calculate a t-value and then a p-value, which will tell us the probability of the data under the null hypothesis. So how would you do that? You can do that in many different stats packages, but you guys are going to have a crack at it in Excel. So you're going to have a workshop in one of the other modules actually later on this semester, where you're going to have a go at this, and you'll be given some example data and you'll be asked to do the analysis in Excel. In order to do that, you're going to need to turn on a particular option in Excel, which is not totally obvious to find. So I'm just giving you the instructions here, although you will get the instructions in the workshop as well. But when you're in Excel, if you go to File, Options, Add-ins, so here's add-ins, you should get this menu of different things that you can add into Excel, and one of them is called the Analysis Toolpack. So if you click on that and then click Go, it'll give you a bunch of different options within that, one of which is just to turn on, tick the Analysis Toolpack, click OK, and you should magically get a new menu in Excel. So if you go to the Data menu on the ribbon, you should find you've now got this Data Analysis option, which allows you to do a bunch of different things, including a t-test. So when you've got that option, if you click on it, you will find it gives you all kinds of different stats tests that you might want to do. We're going to see regression a bit later on in these lectures, but for the time being we're interested in t-tests, and you'll see that it gives you several different options for a t-test. So it gives you a paired t-test, which I mentioned earlier, which we don't want to do today. And then it gives you the independent samples t-test, which annoyingly is also called a two-sample t-test. So that's the one that we want for this particular lecture. And it does give you two slightly different versions of the two-sample t-test. Don't worry about the difference between these for the time being. Just choose the first of them, which says assuming equal variances. That's going to be the one that we're going to use in order to test our hypothesis about triamterene. Okay, so I've done that for you. I've got some data and I've plugged in, gone through the test in Excel, run a t-test, and I get the following output appears in my Excel workbook. And at first glance it looks a bit complicated, but actually all of the things I've already mentioned are in here. So starting at the top, we've got a little bit about each of the two variables. So these are the two groups, in our case the control patients and the triamterene patients. And it gives you first of all the mean value of blueness in my case for each of the two groups. So we've got more blue in the triamterene group than the control group, but obviously we don't know if that difference could have arisen by chance. That's why we need to calculate a p-value. We've got the variances, which we know we need to know. So that's how much spread there is in each of the two samples. Then we've got the sample size, n. So we met that before. That's just the number of individual patients in each group, and there are 11 in our two groups. And then the next important thing on here is the hypothesized mean difference. So this is saying what is the null hypothesis? And the null hypothesis in our case is that the two samples have equal means because they represent two populations with the same mean. So our hypothesized mean difference is 0. There are some situations in which you might want to put something else in there, but let's not worry about that for the time being. That's what we're hypothesizing in this case. So when you've provided the data, which is summarized here, and told Excel what hypothesis to use, it will spit out a t-value. So it calls it here the t-stat. So that is calculated using that equation that we already saw, and the computer does all the hard work for you and tells you that in this case the t-value is minus 2.2. So let's just think about why it's negative. It's negative because the second mean here is greater than the first mean. So it's negative. It's telling us that the triamterene group has actually got more blue in its urine on average than the control group. but we still don't know if that's significant. The size of the t-value, in this case 2.2, is telling us something about the size of the difference and how likely it is by chance. And the computer can actually then put a p-value on that directly for you. So 2.2 is a fairly big t-value. It's fairly unlikely under the null hypothesis. How unlikely? Well, it's going to tell us by giving us a p-value down here. What does my next slide say? Oh yes, I'm going to explain exactly what this means, how you put a p-value on a t-value now. So let's sort of read down as far as it's given us a t-value, minus 2.29 if you round it. What does that mean? How do we turn that into a p-value? Well, t, this statistic, has known mathematical properties. It behaves in a particular way. It has a distribution that it always follows under the null hypothesis. And that distribution looks remarkably like a normal distribution, actually. It's not the normal distribution, but it's very similar. It's kind of bell-shaped distribution. On average, if the null hypothesis is true, if the drug has no effect, then the t-value you're going to get on average is most likely to be 0, right? So the middle of this curve is centered on 0, because under the null hypothesis, says the drug has no effect, that is going to be the average value of t. Because remember, the value of t is determined by how blue the urine in the two groups is. If there's really no difference, then every time you take two samples, you're going to find by chance there's a little bit of difference, but that is going to be sometimes positive, sometimes negative, and on average it's going to come out as 0. So that's why the expected value of t under the null hypothesis, the average expected value is 0. But there's going to be some spread around that. There's going to be spread around that because every time you take a different random sample, you're going to get a slightly different answer. So that's why we sometimes see negative values of t and sometimes see positive values of t. And our question is, well, we've got a negative value of t of 2.29. Is that the sort of value we'd expect to see under the null hypothesis? And because we know what the distribution looks like under the null hypothesis, we can actually say exactly how likely is it that we would see a value as big as 2.29 if the null hypothesis was true. So minus 2.29 sits down here in the tail of the distribution because it's really quite unlikely under the null hypothesis. Most likely values are close to 0. So we can actually say exactly how likely it is and turn it into a p-value using a computer, but sort of graphically you can visualize on here the central 95% of the distribution. That's where most of the data will lie if the null hypothesis is true. And if the data point that you've got lies in the tiny tails outside that area, what you're saying is there's a less than 5% chance that you would have observed a value like that if the null hypothesis is true. And that tends to be the cutoff we use, the 5% cutoff. So if our true value of t lies in these tiny tails outside the main bit of the distribution, what that's saying is you've observed an event which is less than 5%, has a less than 5% chance of happening if the null hypothesis is true, or p is less than 0.05. Okay, so you don't need to do the maths. The computer will work out p exactly for you. It doesn't even worry about the 95% 5% distinction. It actually goes for a very precise calculation of p. And it gives you two options in the output. It gives you the one-sided p-value and the two-sided p-value. So that's dependent on what your hypothesis was to start with. So in our case, we had a two-sided hypothesis. So the correct p-value is 0.033. So about a 3% chance of observing that t-value of minus 2.29 if the null hypothesis is true. So what we're saying is there's a really quite small probability that you'd get a value as large as 2.29 if the null hypothesis was true. And you can see that graphically in this distribution of t, because you can see that it's a really unlikely event that you get a value that far away from 0. So we can reach a conclusion. What we've got is a tiny p-value, or fairly small p-value. It's below the normal threshold that we use, alpha of 0.05. Once the p-value falls below that, we say, well, it's so unlikely to have happened under the null hypothesis must be wrong. So we reject the null hypothesis, and we conclude that the alternative hypothesis is the best hypothesis we have. And the alternative hypothesis says triamterene really does change the colour of your urine. So that's what we would conclude from this study. And in fact, that is what happens in reality. We know that this drug does turn your urine blue. Okay, so that's the end of that stuff. We're going to take a pause now, and I'm going to come back and tell you about the chi-square test, which is a different way of testing for differences using somewhat different data sets.